Greetings and welcome. In this session, we will discuss about the entrance region theory. This is the first session of the module called as internal flow of the fluid mechanics, which comes after the module fluid dynamics. In this session, we will see the different terms: velocity boundary layer, hydrodynamic entrance region, fully developed region, and pressure drop in entrance region. I acknowledge my sincere thanks to the authors of a fluid mechanics textbook as Dr. Sinjal and Dr. Simbala for being used the diagrams and concepts in this video session. Let us see types of flow. Based on whether the fluid is flowing in a conduit, means pipe, or force over a surface, fluid flows are broadly classified as internal flow and external flow. These two flows can be understood with the help of example. So here is an example of internal flow where the conduit is completely filled with the fluid. This is the example of external flow where the fluid passage is partially filled by the fluid and the flow is partially bounded by solid surface. In order to understand entrance region theory, let us take example of laminar flow. This is a flow of a fluid in a pipe. Now, because of the fluid property called as viscosity, that is a resistance offered by fluid to its flow. Here, the fluid particles in the layer in a contact with the pipe surface completely stop due to no slip condition. Also, here is a friction, and because of this friction, the layer which is at the surface causes the fluid particle in nearby layers to gradually slow down. Now, in order to maintain a consistent mass flow rate through the pipe, the fluid velocity at the midpoint, means at the center line of the pipe, has to increase to compensate for this velocity reduction. Here we can see this number of velocity gradient. So because of the friction and no slip condition, here velocity gradient is formed along the pipe. Now here it happens because of velocity boundary layer. So velocity boundary layer is shown here in this diagram with the red color curve on the both side of the fluid flow. This velocity boundary layer is the region of the flow where the effect of viscous shearing forces due to fluid viscosity are sensed, and it is a hypothetical boundary surface which divides this whole region into two parts or two regions. First is a boundary layer region, upper side and lower side, in which viscous effects and velocity changes are significant. That is why here we find, because of viscous effects, here we find the layers with a different velocity. And the second region, that is a central, which is called as inviscid core, where frictional effects are negligible. And that is why here we find velocity remains constant. Now here, if you observe, this velocity boundary layer starts at the entrance and it is proceeding in a forward direction. At a particular location, these velocity boundary layers are merged at the center line. This region is called as hydrodynamic entrance region. So, in hydrodynamic entrance region, we find that this is a graph of this shear stress, that is a variation, and this is the variation of velocity. So, the distance from the entrance to the location where both velocity boundary layers are merged at the center line, this is called as hydrodynamic entry length. It is denoted by letter LH. This LH usually taken as a distance from the entrance of the pipe to where the wall shear stress reaches about 2% of the fully developed value. Now here, for the calculation purpose, two relations are given. For laminar flow, LH can be calculated with this formula, that is LH is nearly equal to 0.05 times Reynolds number and diameter. For a turbulent flow, it is given nearly equal to 10 times diameter. Now, flow in this region is called as hydrodynamic developing flow, because this is the region where velocity profile is developing. Beyond this location, we find the gradient, velocity gradient, that is unchanged. And that is why such region is called as fully developed flow region. So hydrodynamically fully developed region is the region beyond the entrance region in which velocity profile is fully developed and remains unchanged. Nature of velocity profile in the fully developed flow region is a parabolic for laminar flow, and for turbulent flow it is a flatter. In this case, shear stress at the pipe wall is related to the slope of the velocity profile at the surface. Now, as velocity gradient is unchanged, that is why shear stress also remains constant in this region, that is fully developed flow region. Now, in this diagram, the wall shear stress is a maximum at the pipe surface because of what? No slip condition. And boundary layer, which is starting at the entrance region, if you see, thickness of boundary layer is also smallest. Now thickness means what? Thickness means distance of that boundary layer from the pipe surface. Now as the fluid flow is proceeding, shear stress is decreasing and thickness of this boundary layer is increasing. Now because of shear stress at the entrance region, more pressure drop occurs at the entrance, and because of this higher pressure drop, it increases the average friction factor for the entire pipe. Now, for the analysis purpose, it is suggested that to use the region beyond this entrance region, hydrodynamic entrance region, because in this region we find fully developed flow. Means in this region the velocity gradient remains unchanged. So that is why it is suggested to do the analysis of a fluid flow in fully developed region. So this is what importance of entrance region theory. So in this session we have seen about the entrance region theory and different terms as a velocity boundary layer, hydrodynamic fluid flow region, pressure drop which is occurring in entrance region. Let us meet in the next video session. Thank you.